Hi everyone. So we'd like to take a look at what sine and cosine and tangent really are, where they came from, or how they created the sine and cosine and tangent ratios. And those are what our calculators are programmed, and before we used to use a little chart. So in the end, we're going to see that we're really looking at our comparisons. We're going to be comparing in sine the opposite compared to the hypotenuse. And really we could look at the decimal as a percentage. Same with cosine. It's the percentage of how much is the adjacent side compared to the hypotenuse. So another thing you'll learn in higher math is sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. So tangent is actually a combination of both. It's really sine divided by cosine. But you'll get into that in higher math. So the word sine, I looked it up, I was interested. It said that the word sine had to do with a curve. So the word sine comes from Latin, and it's fold in a garment or a bend or a curve. So that makes complete sense as you understand higher math uses sine waves. And those are the waves we use in physics, and color is a wave, and electricity goes in a wave. Perpendicular to electricity is magnetism. You'll even see, our DNA is in a wave as well. So sounds, we program sound waves. Color comes into your eyes actually as transmitted through waves. Waves are kind of like the information being sent to your eyes, which will tell you what color to see. So that could be why the word sinus is what it is, because it has to do with the curve up here in your face. And the word itis for sinusitis, the word itis in medical terms means swelling. So it just means you have swollen sinuses. Tendinitis means you have swollen tendons. Bronchitis means you have a swollen bronchial glands. So really the word itis just means it's swollen or inflamed. Getting into sine and cosine, there's some really cool moving graphic files. And you can see what we were talking about, that sine is a wave. And if we were to show you at this spot is where sine begins, and then up here is cosine. So this helps us to understand what the words sine and cosine mean, because we learned that two angles that form 90, we call them complementary. So the word cosine really means complementary to sine. When we graph them, we learn later, sine will begin on the bottom, and it'll be a wave. And when we saw the unit circle, that position was right here. Whereas cosine is going to start up here. So you'll see when we learn to graph that in higher math, cosine will start up here. And then it'll be the same wave. It's just starting at a different spot. So really, sine and cosine are pretty much the same, just one of them is shifted over or shifted back. You can see it kind of makes a DNA strand. So these are where we get our ways to program our computers for sound and color and on many other things. And tangent, if we were to graph it, because it's a combination of both, it actually makes these curved type of graphs. So it's not going to produce the same kind of wave. It's curvy, but it's not the same kind of wave. Looking at the unit circle like we just did, what you begin to notice is this is kind of the beginning of how we began to understand the triangles. I teach my class, the circle's 360, and we focus on 180. That all of this up here is 180. Even if you cut it into 2 angles, they still add up to 180. Cut it in 3 angles, it still adds up to 180. Then we start to focus on cutting it again, 90. Right? Then we study the special triangle. So if we cut it again in half, now we have the 45, 45, 90 triangles. We're going to talk about that. We learned that the two sides are the same. Then we looked at and learned the 30, 60, 90. So it's actually 1/3 of the way. And it's used a lot in construction, or 2/3 of the way will also work. So if we stop that spinning dot at one position, we can stop it and draw a triangle. So that unit circle is the foundations of our understanding of angles in right triangles. So you could imagine at some point someone had to create a triangle, and what we did is we created, oops, that's terrible, protractor to be able to measure degrees, right? And so we would use this in class, and up here is 90, and we could measure each degree. So even that it's half of a circle. So if I wanted to measure 1 degree, it would be very, very tiny over here to make the triangle. It would be very skinny. And of course, it's probably more than 1 degree. So what if I stopped it up here at, like, here's 45 we said. So let's say 70 or 80 degrees would be up here. So we can draw that right triangle again. So the unit circle is kind of the foundations of understanding each degree. We can take a big old long string and measure what happens when there's 1 degree. And we can create a comparison. So if we use tangent, we learned it's opposite over adjacent. So we're going to compare those two sides, opposite side and the adjacent side. This opposite compared to this adjacent, if we're using this angle here, right? So then they had to do 2 degrees, make it a little bigger. I'm exaggerating, it's way bigger than 2. 3 degrees, do a triangle, 4 degrees, and compare them, 5 degrees. So they went through every single degree and compared the sides. So what do I mean about comparing the sides and how we created these ratios? Well, a good example would be a 45, 45, 90, because we've understood and learned it. And it's the triangle that's isosceles, meaning 2 angles are the same and 2 sides are the same. So we learned the 2 sides are congruent. They're a 1-to-1 ratio. And we could even do the Pythagorean theorem to prove that the hypotenuse will be radical 2. Square root both sides. Oops. So x is radical 2. So these are the proportions we learned in 45, 45, 90 triangles. 1, 1, radical 2. So let's use this to help us better understand how we came up with these decimals and whole numbers we get that we punch into our calculator. So let's pretend you're going to look at the angle x here. So let's use tangent, it'll be easier, is opposite over adjacent. So what we learned is that if I want to find tangent of an angle, tangent of that angle x, I can use the opposite side. That will be this one. Because we learned to label. So if our x is here, our hypotenuse we can label, it never changes. It's across from the 90. Which would make the angle x here, the opposite of it would be the 1. And next to it, but not the hypotenuse, is the adjacent. That would be this one. So we're going to do the opposite side and we're going to divide it by the adjacent side. And in this case, right, it's going to be 1-to-1. So what this is telling us, let's turn this into a percentage. So what we learned is that if you can move your decimal spot 2 places, it turns it into a percent. So what that's telling us is whatever the opposite side is, the yellow one, the blue one has to be 100%. Or it is, in this case, 100%. So we're kind of asking what angle is that when the sides are the same. And we've learned that it's 45 degrees. But somebody wrote that down and they had to write it down for every degree. Figure out what are the comparisons of sides. For sine, opposite compared to hypotenuse. For cosine, adjacent compared to hypotenuse. And for tangent, opposite. We're comparing to the adjacent. So what we have is this chart in the old days, and we would look for when is tangent 1, because we just put it in the calculator. When is the opposite side divided by the adjacent side equal to 100%? They're both the same. And we would look under the column here that says tangent. We're going to have to go down, down, down until we find the number 1. And it's right on the bottom. So when the opposite divided by the adjacent is 100%, or 1-to-1, how many degrees is that? And we know the answer because we use this particular triangle because we know the answer ahead of time, 45 degrees. So someone compared the opposite and the adjacent for every degree in order to try to make this chart. So what would the comparison be of tangent at 1 degree? We kind of use that example. So at 1 degree, 1, it would be 0.017. So what we just said was 0.017 as a percentage. We're going to move that over and it will get 1.7%. So somebody analyzed a 1-degree triangle, and they found that the opposite, comparing it to the adjacent, right, the opposite will be way shorter, and it will always be exactly 1.7%. When we look at that here, we could ask what happens when the triangle gets bigger, right? So what if we make it 10 times bigger? Well, it'll still be 10 and 10. And when we are finding the missing x, now we'll write tangent of x is opposite 10 over 10. So we still get 100%. Why? Well, it's because these are similar. Every 45, 45, 90 triangle is similar to every other one. So the sides will be 100% of each other. They will always be the same. Even if we made it 100, 100 divided by 100 will be 1. So someone figured out that every time you have a 45-degree angle, the sides are the same, and every time the opposite is true. When the sides are the same, your angle is 45 degrees. And your calculator spits that out and tells you that when you enter the decimal. So let's try a slightly more complicated one. Another special triangle we learned is the 30, 60, 90. And what we learned was that the 30 degrees is across from the smallest side, smallest angles, across from the smallest side. Please excuse the crooked triangle. The 60 degrees we learn is across from the longer of the two sides. And then obviously the right angle across from that is always the hypotenuse. So what we learned is that the small side compared to the hypotenuse is always 1 to 2 ratio, or the hypotenuse is always twice as big. So let's make some 30, 60, 90 triangles. Well, if this was 5, I know that the hypotenuse will be 10. What if I made a bigger one? If this was 80, I got to double it, right? So 160. So we're going to know whenever we have that comparison, there's going to be the same angle there. The same 60 degrees will be here. So someone went through every single degree, starting at 1, and they had to measure the matching side. So in this case, what are we looking at? In this case, let's look at sine. Sine of x, let's pretend we don't know it, will equal, oh no, it's going to be actually cosine. I'm looking now. Well, let's get a whole new problem. So we'll put the x here. We want to find out how many degrees is that. And we have a 1 here, or let's make it a number 100 here and a 200 here. So when we label this, we'll see that the opposite is here, the hypotenuse is here, and the adjacent is the 100. So when we are trying to decide if we use sine or cosine or tangent, many people will quickly jot down so, ca, and toa to remember the ratios. And we're looking at a hypotenuse and adjacent. That would be cosine. So let's write down cosine of that angle. We don't know what it is, but we really do. It's 60. But we're pretending we don't know. And someone compared the adjacent was 100 as opposed to the hypotenuse was 200. And when they get that in a calculator, they're going to get 0.5. So what that's saying is if we move the decimal twice, we have 50%. So what we learned in 30, 60, 90 is that the small one is always 50% of the hypotenuse. And so when we look at the chart, it's going to tell us that missing angle if we didn't know it. So let's look at the chart. We just said cosine and then 50% or 0.5. So in this case, we need to notice the chart, right? Sine, cosine, tangent. So tangent is not the one we're using. We're looking at cosine this time. And we just finished asking, when is cosine going to equal 50%? And here it is, 50.5 under the cosine tab. And we look to the degrees, and it's 60 degrees. So someone went through the 1 degree, let's say for tangent, and they measured the opposite and the adjacent, and they wrote down the percentage. Somebody did every single 2 degrees and then did that, 3 degrees, 4 degrees. Maybe you did 72 degrees. So the opposite divided by the adjacent, if we're using tangent, we would look for 72 degrees and know that it would always be 3.07, so 307% bigger, and you can kind of see it. It's a sketch, it's not to scale, but it looks more than 3 times bigger. So someone made a comparison of all the sides for all the opposite and hypotenuse for sine, all the opposite and adjacent for tangent, and all the adjacent and hypotenuse for cosine. And they recorded it, wrote it down, and we programmed our calculators now. So let's look at one of the other examples here with 80 and 60. If I didn't know that angle, and I thought it was x, we would write a similar problem, right? We would say cosine of x equals the adjacent, which is 80 over 160. And we also get 0.5. So it's 50%. So if the adjacent compared to the hypotenuse is half, we always know it's going to be a 60-degree angle. So we went through and made sure we understood every single degree and made it handily available so everyone doesn't have to always measure it every time we build something. So it was a lot of labor and work to understand the sides, and so it's interesting to me that understanding these sides helped us understand triangles, but then when we combine them together, we have curves, and it opens up a whole field of science. So just to kind of recap, when I say tangent of an angle is 0.67, whatever, I'm really saying, since tangent is opposite over adjacent, I'm saying that the opposite side comparing to the adjacent is going to be 67%. So what that might mean if I drew a triangle is that the opposite one here, right, it's going to be less, like 67%, compared to the blue one. So if we used an easy number, right, if this was 100, this would have to be 67. And we can check on the chart, when is tangent 0.67? And the chart will tell us, here's tangent, 0.67 is about right here at 34 degrees. So again, knowing the comparisons of the sides and using these charts or your calculator help us to find a missing angle or the reverse. If I know the angle, I could know the percentage of the sides for each of the 3 ratios. So, I know it takes a little bit of discipline to get through this because it's not the most fascinating to some people, but to me it is fascinating because as we begin to understand this, it opens up the whole world of waves and space and all of these other things that we've begun to explore and understand. And, our computers do a lot of these things and we just don't think about it. We take it for granted. But even more than our computers, someone had to go through each of these ratios for every degree and find out how much percentage is this side compared to that side, and make a chart. And then, of course, thank goodness, eventually we were able to make calculators that do that for us. So all in all, the sine and cosine and tangent comparison ratios are giving us what percentage our side is this one compared to that one. And those will always match up with certain angles and certain degrees, but it's an interesting understanding of where sine and cosine came from and how they sort of began to chart it down and record it for us to use. So hopefully for some of you that makes a little bit of sense. For me at least, even knowing the word sine means the curve makes total sense. And a lot of times I'll look up the Latin or Greek words like hypotenuse. Hypotenuse means like underneath the right angle. And that's basically, if we rotated it, right, the hypotenuse is always across from or underneath the right angle. And when I learn that, it just helps me remember better. So sometimes knowing where things came from, the root of the word, it's called etymology, it helps you to remember or understand what something is. Have a good day. Take care.